The most powerful earthquake sequence in North American history didn't happen in California. It happened in the central United States in the winter of 1811-1812. We know that at least 3,000 earthquakes were associated with the sequence in the winter of 1811-1812, including 3 very large earthquakes near 8.0 or better, and 1 large aftershock close to 7.5. We know that it takes at least a 6.0 magnitude earthquake if it happens in New Madrid, Missouri. It needs to be at least a 6.0 magnitude for it to be felt on the eastern seaboard at the coast of the Atlantic in the United States. Well, we know that 18 of these events were felt along the Atlantic seaboard. That means that at least 18 of the events were 6.0 or greater. This is unprecedented in plate boundary settings, that where most of the world's earthquakes occur. That's why that this is the New Madrid seismic zone in the central U.S. is probably the greatest enigma that scientists, the greatest mystery that scientists face, earth scientists face today.
Reelfoot Lake is a dammed lake, and it's dammed by the earthquake. When the earthquake rose about 2 meters during that third earthquake, it essentially dammed the water behind there, and so now the lake forms a permanent reminder of that large earthquake.
To really explain earthquakes, we have to talk about plate tectonics.
Well, plate tectonics is a theory that was developed and confirmed by observations in about the late 60s and early 70s. And its main sort of set of tenets is that the Earth's crust is divided into a number of rigid shells, so that the oceans in the Earth are produced by seafloor spreading, and mountains in general tend to be where plates are colliding.
It's kind of like, if we talked about the Earth, we would think of it kind of like a hard-boiled egg, that the Earth has a solid inner core, a liquid outer core, kind of a plastic zone called the mantle, which is very thick, and then a very, very thin crust, which would be analogous to the shell of the egg. I'll also imagine that the shell of the egg is broken up into pieces. These pieces are moving independently of one another.
Other sets of mountains like Hawaii and volcanoes in the middle of these plates, they are the result of what are called hotspots, which is much like the plate is moving over, say, a candle flame, and the candle flame is burning through the plate. Volcanoes that rim the Pacific Ocean, those mark the places where the plates are being subducted or swallowed back inside the Earth.
Unfortunately, these plates aren't nice, square little things. They're very, very intricate puzzle pieces. So just because we push out in one place doesn't mean that all the forces are very easy to model or very easy to figure out which way the plates are pushing against each other. We know that the plates are moving independent of one another. So their motions are different because of different factors, mostly because of the edges of the plates aren't square, so they push against each other. That makes the other side spin around. This is the general cause for earthquakes, this movement at plate boundaries. When is the big one coming? Well, I wish we could answer that. No one really knows when the big one comes. We've got some probabilities based on those large events that we've seen in the past that tells us that large 8.0, 1811 type events occur. Some people think every 500 years. Some people think every 1,000 years. A couple of people think every 10,000 years. We don't really know. We can't predict it.
One of the things that we do here at the Earthquake Center to try to understand and try to sort of estimate when earthquakes might happen is to gather all sorts of information.
What we do is locate those earthquakes on our seismic network. Our seismic network is partly comprised from helicorders or seismographs. One seismograph measures the vibrations up and down. One helicorder measures the vibrations going north and south, and the other one east and west. This type of information gives us vital information, vital data on assessing the focal mechanism, the type of energy expressed at the fault at the time of the earthquake, what caused the earthquake, how deep was the earthquake. This data is in turn fed into our computer and also sent to national and international computers so that everyone can see our data. Everyone can see our data in near real time. Very quickly, they can see the earthquakes as they occur here.
I think it's important to realize that although our measurements are often measuring very, very small minutiae of displacements, these GPS satellites measure our control points to a millimeter of accuracy. And you might think, who cares about a millimeter of accuracy in our day-to-day lives? But those very small measurements do tell us a great deal about what happens deeper in the crust of the Earth, and that's where earthquakes are generated. And of course, once those earthquakes are generated, they have a very significant impact on our day-to-day lives. And so trying to really pin down where the deformation is occurring, and conversely, where it's not occurring, it's very important to people like insurance companies or developers who want to know, should they build a certain building here? Or should they put a bridge here? Or should they put it somewhere else? So 1 millimeter of measurement might save literally billions of dollars down the road.